So in this video we're going to look at vector scaling, and let's start with an arrow. So an arrow can be said to represent a vector, and in this case the vector that we've got is, well, it's defined as 3 along and 1 down. It has then a direction going downwards here, so we have a clear direction which can be expressed as an angle, and it has a magnitude which we find by Pythagoras. So it has both magnitude and direction, and that's what defines a vector. Now what we're going to do in this video is we're going to scale up that vector. In other words, we're going to make it larger, and to do that we're going to use an ordinary number, in other words a scalar quantity. So vector scaling is simply when we take a scalar quantity, a scalar, and multiply that by a vector. So it's a scalar multiplied by a vector. Now let's go back to our arrow and see how that works. So we've now got this vector which I'm going to multiply by the ordinary scalar quantity 3. So let's just think what we would do here. If we were to double it, then we would add another vector, and when we add vectors, as we'll see in a later video, all we do is put them tip to tail. So we take the tail of the new one, add it to the tip of the old one, and then we've doubled our vector. If we're going to treble it, so multiply by 3, then we're going to do the same operation again. And what we're doing, of course, is we're just stretching our vector, you could say. So the resultant vector is this, and if I move it down so that we can see it very clearly, you can see now this scaled up vector, which is what happens when we multiply any vector by an ordinary number. Okay, now let's express that mathematically. So what have we done? We've taken an ordinary number 3, and we're multiplying by a vector, which we can express in various ways. I'm just going to use a column vector notation. So our original vector was 3 along and 1 down, so we write that 3 minus 1. And our resultant vector is, well, how many along? It's going to be 3 of these 3. So it's going to be 9 along. And how many down? Well, it's going to be 3 of these negative 1s. So in other words, we can simply multiply these numbers here. 3 of these 3s gives us 9, and 3 of these negative 1s gives us minus 3, or negative 3. So that's all there is to it. A pretty straightforward and intuitive operation, even though we're working in the slightly odd world of vectors. Okay, now what would happen if we scaled down? How would we scale down? Well, all we do then is multiply by a fraction. So let's draw out another vector. So if I draw that down here, what have we got? We've got 2, 4, 6, 8, 10. So we've got a vector that's 10 in the horizontal direction. So it's a positive 10, so it moves to the right. So 10. And it goes 4 up. 1, 2, 3, 4, 4 up. So it's a 10, 4 vector. So there's our vector. And using the same principle here, then, if we're going to divide by 4, we're going to quarter. We're going to multiply by a quarter. And let's see what result we would get mathematically, and then check it on our diagram. So a quarter of 10 is going to be 2.5. And a quarter of 4 is 1. So our resultant vector should be 2.5 along and 1 up. So 2.5 to the right and 1 up. So in other words, from here it will go 2.5 along, 1 up. The end point should be there, so that's going to be the tip of our arrow. So if I draw that along there now, we can see our resultant vector. Now, before I put it off the diagram, let's just check that this makes sense. If I've drawn a quarter of my original vector, as my new vector is a quarter of the original, then I should be able to get 4 of those into the original. So if I draw another one exactly the same magnitude, pointing exactly the same direction, so from the tip, now draw it up to here, so that's doubled, and if I triple it, and now I multiply by 4, so I've got 4 of them now, then what I've done then is demonstrate that this does get back to my original vector. So the operation must be correct, and this then is our resultant vector, 2.51. Okay, now what I'm going to do is think about something else we might do. So if we've looked at whole numbers, we've looked at fractions, what if we multiply by a negative number? So let's take the same vector that we had here, so 3 along, 1 down, and this time I'm going to think about multiplying by, well, let's just start with -1. So -1 times 3, -1. Okay, so that should be a 1. Okay, so if I'm multiplying by -1, and I use the method that I've developed here, I'm simply going to take -1 and multiply by each of the numbers in the brackets. So -1 times 3 is going to give me -3, and -1 times -1 is +1. So I end up with the resultant -3, 1. Now, if I draw that out of my diagram, what would that look like? Well, -3 is our first number, that's a long number. So it means from here, I will go 1, 2, 3 in the negative direction, in other words to the left, and my 1 here refers to going up 1. So what have I done? If I draw my arrow to here, I've in fact reversed the direction of the arrow. So multiplying by -1 reverses the direction. That's a bit neater. Okay, now what happens if I multiply by -3? Well, you won't be at all surprised to hear, there we go, that multiplying by -3 will give me also a reverse direction. But at the same time, it will stretch the vector. So -3 times 3 is going to give me -9, and -3 times -1 is going to give me a positive 3. There we go. So my resultant vector is going to be -9, 3, which we can draw along here. And you could say that this is like 2 operations. First of all, we can just cover up the -1 and say, well, first of all, it's a scalar just as we did before. It becomes 9, -3. But then if we multiply by the -1, that gives us our reverse direction, which means changing these signs. So the 9 becomes -9 and the 3 becomes -3. And the result that produces is, if you like, a velocity or a displacement in the opposite direction. So it stays parallel, but the direction simply flips to go the other way. Okay, finally, what I want to look at is something that we call the zero vector. And we get a zero vector when we multiply, and I don't think I'm going to draw it, I will simply write it down, when we multiply by 0. So if we multiply by 0, let's keep the same numbers, so we've got 3, -1. What's going to happen? 0 times 3, well, that's going to give us 0. 0 times 3 is 0. And 0 times -1 is also 0. So we get a 0, 0 vector. And that's a result called the zero vector. What does it mean graphically? Well, if we start from this point here and think about what happens within the zero vector, it goes along 0. So what does that mean? It means it doesn't go along at all. It means it doesn't go to the right, it doesn't go to the left, it just, if you like, stays put. It's just here. What happens vertically? Well, exactly the same. It doesn't go up, it doesn't go down. So what can we say about the zero vector? It's quite an unusual beast. We can say that it has no magnitude because it has no size. It doesn't have any length, if you like, in our graphic here. And we can say that it has no direction either. We can't say that it goes to the left or the right or at any angle. So it's a rather unusual equivalent of 0, if you like, in the world of vectors. It's a rather unusual vector in that it has no magnitude and no direction. Nevertheless, it's very important. It's a very useful thing in more advanced vector mathematics. So it's an important idea to just think about the zero vector, the vector that has no magnitude, no direction. Now, an important idea involved here that sort of comes out of this idea of scaling is you'll have noticed that when I drew out these diagrams, all of these lines are parallel to one another. So when we scale something, in other words, we end up with parallel lines. In other words, the lines always go in the same direction or in the opposite direction. Now, if they go in the opposite direction, they're still, of course, parallel. So they're still going, as it were, in the same line. So parallel lines are a very important idea in vector analysis. And what we're going to do in the second part of this video is look at how we can use something called the dot product to check whether two lines are parallel or not. Okay, so here we've got two vectors. We've got the 3, -1 that we had before, and we've got the scaled up version 9, -3. Now we know these are parallel, but I'm just using this as an example to check what we're going to do next. We're going to use the idea of the dot product. Now the idea of the dot product is that when you've got any vector, A, and you're kind of multiplying, although the algebra of vectors is very different. Whoops, that should be in line. It's very different, so it's not exactly out multiplying. What you're doing, in fact, is you're taking the first component, so these numbers here, the 3 and the 9, multiplying them together and then adding them to the product of the second number. So taking the -1 and the -3 here, you'll see how this works in just a second. It's a very easy operation to do. So that's the dot product. And the little rule we're going to follow here says that when you do that, that's exactly equal to the magnitude of those two vectors, the magnitude of these two vectors, which we write like this, so how big they are, multiplied together, multiplied by, and here's a bit of trigonometry, the cosine of the angle between the two vectors. That sounds complicated, but actually very simple to use in practice, and you'll see how it works in just one second. Okay, let's just change the color here, there, and work this through. So first of all, let's find the dot product of these two numbers here. So the dot product, as I say, is when we multiply the first two components. So it's going to be A dot B gives us 3 times 9. Well, that's 27. And the second component, -1 times -3, which we add to the first one, gives us +3. So what have we got? Well, we haven't got a vector. When we take the dot product of two vectors, then we don't get a vector, we get a scalar quantity. We get just an ordinary number. So that's the first thing. The dot product doesn't give us a scalar. Now, I'm going to just think about this before I do the next part of the calculation so that you can understand what it is that is so useful about this little formula. And that is, I'm going to rearrange it. So I want to find the angle, because the angle, which we're calling theta, between these two vectors is going to be 0 if they're parallel. So if the angle is 0, what's cos theta going to be? What's cos of 0? Well, the cosine of 0, as you'll know from trigonometry, is 1. So if they're parallel, this whole thing here, the cos of the angle, is going to be just 1, which means it's going to disappear. Which means that the dot product of vectors A and B is going to be equal to the product of the two magnitudes. The magnitudes multiplied together. And that's a very useful idea. Okay, now if you found that a bit difficult to follow, I'm going to say it sort of in a slightly different way. Let's just rearrange this. So if we take our cos theta to be the subject of the equation and we divide by this part of the equation here, we'll end up with cos theta equals vector A, the dot product of vector A and B, divided by the two magnitudes multiplied together. In other words, we end up with this. Okay? And this is the thing that you may want to remember. It's a really useful little thing, very easy to remember because it looks so nice. And what you've got in the numerator then now is the dot product, and in the denominator you've got the two magnitudes multiplied together. So if they're the same, if the dot product and the two magnitudes, the product of the two magnitudes are the same, if these turn out to be the same, then you're going to have the same number divided by the same number equals 1. And if cos theta equals 1, theta must equal 0, and therefore the two vectors must be parallel. So that's the idea that we're working with when we're asking this question: are these two vectors parallel? All right, let's just give it a go, see how that works out in practice. So the very first thing I want to do is find my dot product, which I've already seen is 30. I want to check that that's the same as the two magnitudes multiplied together. So how do I find the magnitude of A? Let's write that here. So magnitude of A, we write like this. Well, we find that out by Pythagoras. So the magnitude of A is the square root of the first component squared. Well, that's going to be 9. Plus the second component squared. Well, that's minus 1 squared. But minus 1 squared is just 1 squared, which is 1. So we've now got the square root of 9 plus 1, which is going to be root 10. And I'm leaving it in exact form because I don't want to get into decimals. Okay, so now let's find the magnitude of B. Let's write that a bit neater. Okay, so the magnitude of B, like that, again is going to be the square root, this time larger numbers. So we've got square root of 9 squared, which is 81, and minus 3 squared, which is going to be the same as 3 squared, which is 9. So what have we got? We've got the square root of 90. And if we understand how to simplify surds, square root of 90 is going to be 3 root 10. Okay, so just pulled the 9 out there, rooted it to become 3, and then we've still got the 10 underneath, so we've got 3 root 10. So what's the product of the two magnitudes, A and B? Well, it's 3, let's say, times root 10 times root 10. We can now join these together to become root 100, and the root of 100 is 10. So we've now got, or we could say that's root 10 squared, which is just 10. So it's 3 times 10, which is 30. And that was the result we were hoping for. So we now know that these two vectors, we knew it before, but we've got to check now that these two vectors, because this one and this one are equal, it must mean that cos theta equals 1. And if cos theta equals 1, then theta must equal 0. In other words, these two are parallel. And if you don't want to worry about this formula, you simply need to remember this, and remember that if these two are equal, then we're going to have parallel vectors. Just a nice little test. Okay, let's have another go. This time, well, let's say if we define our vectors using familiar numbers again. So we'll have 2.5, 1, and our next vector 10, 4. So are these two vectors parallel? Okay, let's start with the dot product. I'll change kind of my pen so you can see the difference here nice and clearly. So the dot product. So we've got vector, oops, not A, vector C. Okay. So vector C, dot product of vector C and vector D. Okay. So dot product, we multiply the two vectors and then add those together to get a scalar. So 2.5 times 10 gives us 25, and 1 times 4 gives us 4. So we get 25 plus 4 equals 29. So that's the numerator in this construction here. And what we're hoping, or what we're wondering if you like, is do we get exactly the same number when we multiply the two magnitudes together? Let's have a look. So, magnitude of C we find by square rooting. Now the numbers are a little bit trickier here. I'm going to change this, in fact, to 5 over 2. So I'm going to turn this into a rational number, a fraction. So 5 over 2. So 2.5 is the same as 5 over 2, simply because that's going to make the calculation easier, and we're going to be able to keep it in exact form. So let's get out of decimals and back into fractions. Okay, so now I need to square 5 over 2. I end up with 25 over 4 plus 1. Okay, so 1 I'm going to express now as 4 over 4. And now resolve what we've got here. We've got root of 29 quarters, or fourths if you like. Root of 29 fourths. Okay, let's leave that for the moment, come back to that. Let's have a look at D. Well, D is going to be easier. We've got the first component squared, so we've got 100, plus the second component squared, we've got 16. So now we've got the square root of 116. Can we simplify these surds? Well, yes, we can. If we think about this as a quarter times 29, then we can take that quarter out and say, well, a half times a half is a quarter. So we end up with a half of root 29. That looks a bit nicer. What have I got here then? Well, if I think of taking a square out of here, can I halve it and halve it again? In other words, can I take 4 out? Well, yes I can. I've got 58, and in fact half of 58 is 29. So now I've got 2 root 29. Let's just check that. If I double 29, I get 58. If I double 58, I get 116. So I've got 2 root 29. Now let's find the product. So if I take my C and D vectors, multiply them together, I get a half times 2 times 29 times root 29 squared, or root 29 times root 29. Root 29 squared is 29, so times 29. Half times 2 is 1, and 1 times 29 is 29. So again, I've proved that they're parallel because I've got the same answer using my product of the two magnitudes, giving me 29. It's giving me the same result as my dot product calculation. If they're the same, then cos theta must be 1. Cos theta is 1, then theta must be 0. Therefore, these are parallel.